So what I want to do now is talk about purely frequency domain filters. Okay. So you have seen already spatial domain filters, right? The box filter, Gaussian, and then so the smoothing filters and sharpening filters. Just can somebody remind me if I posted a lecture on sharpening filters, the Gaussian, Laplacian, not Gaussian, the gradient filter and the Laplacian, and the Sobel, Privet, and the Robert. Did you already have access to those? I think I must have posted uh, a lecture on examples of spatial filters. Okay, well, if you don't remember, I will go back and look at it. But I think I did post something on examples of spatial filters. I just don't remember if Sobel, Privet, and Robert filters were done. Anyway, so if they were not done, I will talk about it later. What I want to do now is talk about purely frequency domain filters. Again, there are two classes. One is the smoothing filters and the other is sharpening filters. Okay. The smoothing filters in this domain are called low pass filters because they allow lower frequencies to pass. And that what's frequency in this case you can translate it to intensities. Okay, so the lower intensities are allowed to pass and that creates a general smoothing effect in the image. And the other class is sharpening filters, where only the higher frequencies are allowed to pass and lower ones are blocked out. And that creates a sharpening effect. Excuse me. So these are the two classes. And in particular, we will look at these filters. Okay, there is something called as the ideal filter, Gaussian, Butterworth. So these are the three that we will discuss today. Okay, and then there are band pass and band reject. So these are like you can define a certain band of frequencies to pass, and the band pass filter will let it pass, and the band reject will block those chosen frequencies. Okay, so these we will see examples of these on Thursday. Today we will just focus on these three. Okay. Now, in the frequency domain, it turns out that these three filters can be made low pass and as well as high pass. Okay, so by correct definition, all three types of filters can be made low pass and high pass. Okay, so we will look at them one by one. So the ideal filter actually is called ideal because theoretically you can define this and it makes sense, but practically it is not possible to design an ideal filter. Okay, so this is something that I don't understand much. This has something to do with the electronics. Okay, so I will try to explain a little bit, but the ideal filter is also called ideal because it results in a very sharp filtering. Okay, and it's very easy to understand what the ideal filter does, but it cannot be accomplished in practice. So ideal filter corresponds to very sharp filtering. On the other hand, the other end of the spectrum is the Gaussian filter, which leads to very smooth filter. Okay, so these are like the ideal filter and the Gaussian filter are like two ends of a spectrum. Okay, and the Butterworth filters are a class of filters that lie between these two ends. Okay, so the Butterworth filter comes with a parameter called the filter order. Okay, the parameter n called the filter order. For a small values of n, the Butterworth filter acts like a Gaussian filter. And for large values of n, the Butterworth filter moves towards becoming an ideal filter. Okay, so these ideas I will show you through graphs a bit later. But all I want to tell you now is that there are these classes of filters. Okay, so the Butterworth filter are a class of intermediate filters depending on this parameter. Okay, you can control how much smoothing or sharpening you want using a Butterworth filter. Okay, so there is one more word that I have mentioned here, that is ringing. Okay, So we will talk a little bit more about ringing. But here what I would like to mention is that the ideal filter causes lot of this artifact. Okay. So it causes noticeable ringing, and it's an artifact that is not desired in images. Okay. So the ideal filter causes this. On the other hand, the Gaussian filter causes no ringing at all. Okay. So this is one of the reasons that make Gaussian filters very desirable. Okay. So there is this artifact does not appear in Gaussian filter. And in Butterworth filtering, well, if you take small parameters and you're close to Gaussian, then you will have no ringing. But if your n increases and you're going more towards ideal, of course, the ringing will be seen. Okay, so it's an effect which is caused by loss of high frequency information, and we will see in images how it looks like. So before I proceed with these filters, there is a small small discussion which should have been done earlier. So I will just I've added it here. So we want to talk about computational advantage of using frequency filters over spatial filters. Okay, so remember, you can do filtering in the spatial domain, and you can do the same filtering in the frequency domain. So this is something I have discussed in the previous posted lecture, I think, how to construct a frequency domain filter, and you can also construct it from a spatial domain filter. So if you can do the same filtering in a spatial domain as well as in the frequency domain, why would one want to go to the frequency domain at all? Okay, so here the comparison between the number of operations required is made here. Okay, so suppose your image size is m cross n, a capital M cross capital N, and the kernel size is small m cross n. Now the cost of convolution in the spatial domain. So your spatial, if you're doing this in the spatial domain, then we have seen earlier that if you have a non-separable spatial kernel, then the number of operations required are given by this. On the other hand, if you have a separable kernel, we have seen that the number of operations comes down to capital M times F plus N. So there is a computational advantage already here. But now, on the other hand, if you do frequency kernel, that is, you're doing convolution in the frequency domain, then it can be shown that the cost of computations is actually only this much. Okay, so this is a really small, slowly increasing quantity as Mn increase. Okay. And so Mn times M plus N and twice Mn. So there is a considerable computational advantage in doing convolution in the frequency domain. Okay. As you might have also noticed when you saw the steps for filtering in the frequency domain, right? You're not doing convolution actually anymore. You're not sliding this window anymore, right? You're just doing multiplication, point-wise multiplication of two matrices. So that considerably brings down the cost. You can, so if you are looking at a square image with a square kernel, okay, then we can quantify this in the following way. So the computational advantage over a non-separable kernel, okay, so this quantity, sorry, here, Mn times Mn. For a non-separable kernel, the number of operations required is m square over capital M square times small m square, and the number of operations required in the frequency domain is these many. Okay, so that computational advantage is given by small m square over 4 log m. And if you are working with a separable spatial kernel, the computational advantage is given by this. Okay, so graphically, if we plot this out, so what is here is over a non-separable kernel. Okay, this comparison of operation counts, and here the comparison is over a separable kernel. Okay, so non-separable kernel in spatial domain versus frequency domain. That's what the first graph is talking about. And on the x-axis you have the size of the kernel. Okay, and this is for a fixed image of size 2048, cross 2048. Your capital M is 2048. So what is this telling us? This is telling us that so on the y-axis they have plotted the computational advantage. So if the filter size is small, okay, then you don't see too much computational advantage. Okay, but as the filter size grows, okay, then there is a steep rise in the computational advantage that you gain by filtering in the frequency domain rather than in the spatial domain. Okay, so for small kernels it's not such a big deal, but when the kernel size grows, then definitely one would want to prefer the frequency domain. This graph here is showing the same kind of comparison, but for a separable kernel. Okay, so for a separable kernel also you can see that for small kernel sizes, so you don't see much computational advantage. Also, the computational advantage here is not as much as the computational advantage here, right? This is CNM times 10 cube. Okay, so this is a huge computational advantage. This is not that huge, but still, when the kernel size increases, again, you can see that you might prefer to work in this frequency domain because there is considerable, if not as huge, there is still considerable computational advantage of working in the frequency domain. Okay, so you can see these numbers. So, for example, if you're working with a non-separable kernel, say of size 7, okay, then this computational advantage is to the order 1. So, essentially, it won't matter. You may work in spatial or frequency domain. Okay, if you're working with this kernel size. But if you go to a kernel size 11, immediately you can see that you are the computational advantage is to the order of 2, which means you might require twice as many operations in the spatial domain than in the frequency domain. Okay, and this number increases pretty fast. Okay, with the increase in the kernel size. Okay, so in fact, it is the case that for kernel sizes more than 7, if you ask NumPy to do some filtering, okay, it will invariably do it in the frequency domain, not in the spatial domain. On the other hand, if you have a separable kernel also, up to size 21 or even 27, it seems to be there seems to be not much computational advantage. But of course, for bigger kernel sizes, you can see there is considerable computational advantage of filtering in the frequency domain rather than doing it in the spatial domain. Okay. So that is computational advantage with respect to the filter options. Okay. But there are also algorithm options. Okay, when you're filtering in the frequency domain, you can either use the discrete Fourier transform plus inverse discrete Fourier transform, or you can use the fast Fourier transform plus inverse fast Fourier transform. Okay, and so I'm not going into the details of the fast Fourier transform. This would be like an entire discussion in itself, maybe 2-3 lectures. And I mean, people who are from an engineering background will already know the importance of a fast Fourier transform. In fact, it has changed. The fast Fourier transform is so ubiquitous, and it has completely changed the way machines work, and a lot of things today are possible because of the fast Fourier transform. So it is one of the most influential algorithms that finds its way into any list of top 10 algorithms that have changed the world. Okay, so fast Fourier transform is one of those algorithms. And so this using FFT over DFT also gives considerable computational advantage. Okay, so here is just an example that if you compute for again this image size and kernel size, if you apply DFT, say for a 2048 by 2048 image, then a DFT doing frequency filtering for this kind of image, okay, comes out to approximately 17 trillion operations. Okay, so that is 17 times 10 raised to 12, these many operations. Okay, and if the same kind of filtering is done using the fast Fourier transform, then this comes out to some 92 times 10 raised to 6. Okay, so you can see the difference in the powers of 10 here. Okay, so that's just to give you a glimpse of the differences in the computational advantage of using FFT over DFT. And nowadays, I mean, unless you specifically ask for DFT, everything will use FFT. So yeah, so these are just a small discussion on computational advantage in the filter options as well as about algorithm options. Okay. Yeah, so now I want to go back to talking about these filters. Are there any questions so far? All right. So let's go back to talking about these filters. Let's begin with the ideal filter. Okay. No, I have a little note about, but this is something that I have already talked about in the previous class, the posted lecture, which was steps for filtering in the frequency domain. Okay. So unless somebody wants me to go over this, I'm going to skip this. Okay. Or maybe we will go over this at the end. Okay. So is this, by the way, for your homework, this has to be clear to you. Have you studied this? Are you looking at the homework problem where I've asked you to, compare filtering in the spatial and frequency domain? I think it's the last exercise in the homework. So I think this part of the notes was specifically for that reason. So is this the process is clear to everybody? How one does filtering in the frequency domain? Okay, so I'm going to take that silence as a yes and move on. Okay, so unless anybody asks me a question, I'm not going to go through this part. Yeah, so let's talk about purely frequency domain based filters, the ideal filter. So let's first look at the low pass versions of all of these, and then we look at their high pass versions. Okay, so the ideal low pass filter, what it does is it passes all. So this is the filter definition. Okay, so I will describe all of this in a moment. But what the ideal low pass filter does is that it passes all frequencies within some circle of fixed radius about the origin. Okay, so it will pass all frequencies here and block everything outside. That is what this filter definition is saying. So what is it doing? Your D naught is some fixed number. Okay, a choice of D naught is done right at the beginning. So this is a fixed number. DUV is nothing but the radius. Okay, so yeah, but radius with respect to what? So one has to be a little careful. So DUV is the distance of the point UV from the center of the frequency rectangle P by 2 Q by 2. So I hope that you have gone through the previous lecture and you know that in the frequency domain, we always prefer to, so if you're looking at a rectangle of size P by Q, okay, then we always prefer not to have the frequency image centered here, but centered here, right? And so this is the center of the frequency rectangle, okay, and that is what I mean by center here also. So this is the center of the frequency rectangle. It has coordinates P by 2, Q by 2, and UV is any other, or U naught, V naught is any other point here. So this distance is exactly what DUV is. So if this distance is less than a decided D naught, then you set the filter to 1, else you set it to 0. That is what the ideal low pass filter does. It's exactly what I described earlier. So now if you want to see a sort of pictorial depiction of this, if this matrix or this array of numbers is displayed as an image, then this central image, this is what it's going to look like, right? So all the entries here are 1 and entries outside are 0. So this is just the pictorial depiction of this array, okay, or this ideal low pass filter. But a more useful image to keep in mind is this, where this is a perspective plot. Okay, so uh, uh, on the plane here in the UV plane, okay, so these are all these pixels which lie in the UV plane, right? I shouldn't say pixels, I should just say array elements. This is not really, this is not really an image. This is just your filter. So these are all the array elements lying in the UV plane. So these are all 0. And uh, in this circle, these are all 1s. Okay, so that is why you have this sort of 3D plot of this filter. Okay, and if you take a cross section of this plot, then this is what is displayed here. Okay, what this means is that up to D0, the value is assigned as 1, and exactly at D0, the value drops to 0. Okay, for all values greater than D0, values of DUV greater than D0, the filter is assigning 0. And this is exactly what I was mentioning earlier. Why the ideal filter cannot be implemented in practice. So it turns out there are some limitations in electronics that cannot implement this steep drop, okay, or immediate drop. Okay, so if this has to be smoothened out a bit, and then the drop is possible. So this steep drop, for some reason, cannot be implemented, and so the ideal filter cannot be implemented as it is in practice. However, this idea theoretically is useful to describe the ideas that come later also. Okay, so just understand what these three images mean. Okay, so this is nothing but the image depiction of this array. Okay, just for this is all for understanding purposes. This is the 3D depiction. Okay, and this is the 2D depiction if you take a cross section. So in these different ways you can view sorry, the action of the filter. Okay, but now what is important for us is also to see what this is going to do in the frequency domain. Okay, so this if we just look at small radius, so that's what is being done here. This radius is small, so this is an ideal low pass filter. Okay, and this is its image in the spatial domain. Okay, so think of this ideal low pass filter as an image in the spatial domain. Then you can take its frequency image, right? You can transfer this to the frequency domain. So if this image, you look at its frequency information, it looks like this. Okay, and why does one want to do this? Because if you look at the frequency information contained in the image of the ideal filter, then these rings here sort of explain what this phenomena of ringing is. Okay, okay. So what is being done here? You have applied discrete Fourier transform this image and converted that image into the frequency domain, and this is how it appears. If you take a cross section, or if you look at the intensity plot of this along a horizontal scan line, then this is what it looks like, right? So you have some frequencies here, and then the intensity is increasing, and the intensity at the center is really high, and then it goes decreasing again, right? So this is exactly the intensity plot over a horizontal scan line. And this phenomenon is what causes this artifact of ringing in images, which you can see here. So this is the original image. Okay, so forget about this. This is the complete blurring. But if you look here, okay, so we want to smoothen this. We want to blur this image using the ideal low pass filter. So this A here, look at what's happening here. So you have smoothing, of course. You can see smoothing everywhere. But look at the edge. Okay, you see this ghost-like white pixels appearing around A or around every object, right? I've just marked out 2 here, but you can see around every object there is this white pixels appearance of white pixels. Okay, that happens exactly because of this ripple effect that you're seeing here. Okay, so this is not just one band of white pixels. This is these white pixels in decreasing intensities around it. Okay, so what happens is when this filter is applied to the edge where there is a where the action really happens. Okay, uh, when the intensities are changing, that's where the blurring really takes place. Then, because of this kind of behavior of the frequencies in the filter, you get this kind of effect in the image. Okay? So this image has been obtained with a filter of size. So they have mentioned it here. Filtering with cutoff frequencies set at radii of 10, 30, 60, 160, 460. So this here, what it means is that the D naught is 10. The radius of the ideal filter is 10. Okay, that radius determines the size of this circle. Okay, and so what they've done is they've taken a small one, radius 10, then radius 30, 60, and so on. Right, so various radii they have taken. So the smallest one, the smallest ideal filter, is giving you this. Oh, sorry, the smallest one is 10, and that gives you this, the maximum blurring. Okay. This one corresponds to 10, 30. Okay, so this corresponds to radius 30. This corresponds to radius 60. So now the radius of that circle in the ideal filter is increased, and you still see this effect. Okay, you see this effect around the edges of all the objects. This effect is called the ringing effect, okay, or just ringing. Now the filter size has been increased even more, so increased to 160. Okay. So here now you don't see that effect so much. Now that ringing effect has disappeared here. Okay, but so has the blurring. See this now. Now this circle size is 160 pixels, much larger than this 60 pixels. Okay, so you don't see as much smoothing happening here now. Okay, and this one is with 460 pixels. The radius is 460 pixels. So that's a really, I mean, the image itself is 688 by 688. Okay, and now you're taking filtering with a ideal filter of radius 460. There's almost no blurring happening here. Okay, so there are two things that I want you to note from here. One is, of course, this ringing effect, okay, that comes about with this ideal filter, exactly because its frequency information is of this form. Okay, the frequencies in the ideal filter are like this. So that is why this ringing effect is coming by. The other thing that I want you to note is that how much blurring comes by because of the radii of those filters, okay, or the what is it called, the cutoff frequency. Okay, so the cutoff frequency here was 10, right? So this one is with cutoff frequency 10, this one is with cutoff frequency 30, this image is with cutoff frequency 60, this image is with cutoff frequency 160, and this image is with cutoff frequency 460. And notice the blurring proportion. When you have a small radius, you see the most blurring, right? And now when the radius is increasing, the blurring effect becomes lesser and lesser. And in fact, when the radius is so large, you can almost make, I mean, this image looks almost like the original image. You don't see any blurring happening at all, right? So this inverse proportionality of filter cutoff frequency and blurring effect. Okay, so smaller your cutoff frequency, more the blurring effect. This inverse proportionality is a comes from the mathematical properties of this Fourier series. Okay, so again, that is something we are not going too much into, but it is a point to note. Okay, and it will come up again in the remaining filters also. So two things, ringing and this inverse relationship between filter size or cutoff frequency and blurring. Okay. Any questions at this point? Okay, if not, then we can move ahead. Yeah, the aim of a good low pass filter is to achieve blurring with little or no ringing. So as I mentioned, this is not something that is desirable in a filtered image. Okay, not just because it doesn't look good, but also because if you want to go ahead and do segmentation or any other processing with this, these pixels will are giving you false intensity values. Okay, so that it's going to mess up your segmentation later. So this is definitely something that is not desired. Uh, and the filter that achieves this, no ringing, is the Gaussian filter. Okay, so the Gaussian low pass filter is defined in this way. Uh, Again, we have the same DUV, okay, that we defined earlier, and a cutoff frequency D naught. Commonly, this cutoff frequency is taken to be the sigma in the definition of the Gaussian. Okay, I haven't put any coefficient here, just for simplicity. So HUV equal to e raised to minus d square UV divided by 2 sigma square. Okay, this is the definition of the low pass Gaussian filter. Okay, uh, and this is how it looks like. So, uh, well, everybody knows that this is going to be centered around the that same frequency rectangle PQ, right? Centered around this frequency, the center of the frequency rectangle. Okay, so that is why if you take that as an image, if you look at this Gaussian filter as an image, then this is what it's going to look like, right? So its highest frequency is going to be at the center of the rectangle, and the frequencies are going to decrease according to this Gaussian, gradually decrease, and they are going to be zeros uh, at the outer edge here. Okay, so this gradual decrease is the blur that you see in the image of the Gaussian filter. A cross section of this looks like this. Okay, and they have displayed it for various values of D naught. Okay, when the D naught is small, notice when D naught is small, you will have a tighter rise here. Okay, that means you are going to have a smaller circle here. Smaller circle corresponds to more blurring. The same inverse proportionality holds for all these filters. So when your D naught is small, which means when this circle is small, then the blurring is going to be much more. And as the D naught increases, which means the radius of this circle gradually increases, or the spread of the Gaussian increases, okay, then the blurring is going to be less and less noticeable. So here are so what they have done is they have taken Gaussian filters of these approximately these radii or these cutoff frequencies. Okay, and these are the images. And see, the thing to note here now is that in the Gaussian blurring there is no ringing effect. Okay, because I mean, uh, if you display this image in its frequency, or if you apply DFT to this and display in the frequency domain, then uh, I mean, this appears exactly like this. It's a Gaussian because the Fourier transform of a Gaussian is a Gaussian. Okay, so you don't see these kind of ripples. Okay, the Fourier transform of this is going to be a Gaussian again. So there are no ripples, and therefore there is no ringing. Okay, so in a Gaussian blur, you will not see any such. And so that is why Gaussian blur is the most preferred way of blurring an image. Okay, and again here they have shown for different cutoff frequencies the effects of different Gaussian low pass filters. Okay, and then we look at the class of Butterworth low pass filters. So Butterworth low pass filters are defined as HUV equal to 1 over 1 plus, I don't need this one, DUV over D naught raised to twice n. So this is the, I mean, just the definition of the Butterworth filter. Not that you require it anytime, because well, I mean, NumPy and MATLAB both have these implemented in their standard computer vision library. So it's not that you need to define this anytime, but just to understand the property. So the way, so this looks like, the image of the Butterworth filter looks like this, okay? And notice that we have this parameter n now, okay? So the larger parameter, the larger values of n are going to take us closer to the ideal filter, and smaller values of n are going to take us close to the Gaussian filter. And you can imagine why, because well, if you look at the 3D plot of this function, what happens is that the steepness of this rise increases as n gets larger, okay? And that is also clear here if you look at a cross section. So when n is 1, this is very smooth, okay? The outermost here is n equal to 1, and then as n becomes larger, you see this becoming more so this sort of this reflected S shape, okay? And when n is really large, this will become closer and closer to the ideal filter, okay? So this is how, when n is small, this acts almost like the Gaussian, and when n is large, this acts almost like the ideal filter, okay? And so if n is large, what will happen here, I mean, from here you can imagine what's going to happen is you're going to have this 3D plot exactly like that of a ideal filter, which means this blur here is going to become less and less. It is going to become sharper, and then it's going to cause ringing, okay? So for smaller values of n, you will have no ringing. For large values, you will see. So here are the Butterworth filters for different values of n in the frequency domain. Okay, so the images are already in the frequency domain. So this is for a small value of n. So here they have said order 1, 2, 5, and 20 respectively. Order means n parameter value. So order 1, this is almost like the impulse function, right? You just have a white dot here, almost like an impulse. This is the Butterworth filter in the frequency domain for n equal to 1, n equal to 2, n equal to 5, and n equal to 20. And as expected, here you don't see, that is this effect is still very small, so you don't see any ripple. But here the effect becomes more pronounced, okay? And now you can see these ripples around the center, and these are going to cause the ringing in the filtered image. So this is the effect of the Butterworth filter on the same image. Okay. So the small size Butterworth filter, I think they must have said what n is. N is 2.25, so n is quite small. Okay, and so we don't see any, we don't see much ringing appearing here. So this is midway between the ideal and the Gaussian filter. This gives us more control over the filter that we design. So these are the three main low pass filters. Okay. This is another example of why filtering or smoothing is useful. Okay, so here you can see this, or the original image has a number of places where the characters are broken. Okay, and that sort of thing can be gotten rid of by smoothing. Okay, so this is just a simple smoothing with a Gaussian filter, and the gaps are already closed. Okay, and this kind of thing is useful. I mean, not here, but in other places, this kind of thing is useful if you want to again close gaps and threshold. Okay, suppose you are interested in the boundary of this. Okay, if you do thresholding here and start looking for the boundary, these gaps are going to cause problems. Okay, even for later algorithms that we will look at, edge detection algorithms, these gaps cause a problem. Those gaps can be closed by doing a simple filtering in the beginning, smoothing operation, And then now if you do your thresholding and edge detection, it works much better. Okay, so this is an example of why smoothing is desirable. So these were all low pass filters. High pass filters can be obtained from low pass filters by just doing this operation. Okay, so the corresponding high pass filters. So you take any low pass filter and you subtract it from 1. That will give you a high pass filter. So for example, the ideal high pass filter is 1 minus the ideal low pass filter. The Gaussian high pass filter is 1 minus the Gaussian low pass. The Butterworth high pass filter is 1 minus the Butterworth low pass filter. So these are the formulae for those. Okay, and their actions are exactly, or at least the profiles are exactly opposite of that you see in the low pass filtering. Okay, so now here we have zeros in this circle and ones everywhere outside. Okay, so this is 1 minus the inverse image of the low pass filter. And so in 3D the intensity profile looks like this. Okay, and a cross section of this intensity profile is this, which means that up to your threshold or cutoff frequency D0, you're assigning zeros and then ones everywhere else. So this is the ideal high pass, and this is your Gaussian high pass. Okay, the image and the cross section of this 3D plot. This is the Butterworth high pass. Okay, notice that what this is going to do is if you apply this filter to your image, it's going to invert your image also. Okay, so those original images, I'm at the end here, maybe I'll show you from the textbook. So those images that we had earlier are going to be exactly inverted. So this is the effect of applying a high pass filter. Okay, so the background was white and the objects were in black, right? But now applying the high pass filter is going to invert the image. So your background is going to become black. Okay, and only the edges are seen. Okay, so this is what the effect of a high pass filter is. So here they have applied all 3 high pass filters, and the difference in the 2 rows is the cutoff frequency. So in the upper row, the cutoff frequency is 60, lower row cutoff frequency is 160. That's the only difference. These two are with ideal high pass, Gaussian high pass, and these two are with Butterworth high pass. Okay, so here I don't know if the differences are clear. Okay, but the point is that the ringing here again in the ideal high pass filter, you can see the ringing again very clearly. Okay, you have these unwanted frequencies or unwanted pixels appearing around or in that image. Okay, and in the Gaussian, that effect is completely missing. Okay, you can clearly imagine why this kind of filtering might be useful, right? What has been accentuated in this Gaussian after this Gaussian filtering are exactly the edges of all the objects in the image, right? So a high pass filter has blocked out all the lower frequencies and has allowed only the higher frequencies to pass. Higher frequencies occur when there is a sharp change in intensity, and that has exactly caused these edges to stand out. Okay, so if you are interested in edge detection and are not bothered by gaps or something like that, then the thing to do is to apply a high pass filter that will bring out the edges or the corners or the contours in the image. Okay. So this was about all kind of low pass, not all kind actually, 3 kinds of high pass and low pass filters. Okay, so what I want to talk about next are a certain kind of band pass and band reject filters. So actually, I will prefer to talk about this next time because it's not convenient to go back between my notes and the book. Okay. So I will. So next time I will talk about this. There are these band pass and band reject filters and band reject. And these are also called as notch filters. And these do some pretty, these can do some pretty amazing things uh, in the image processing. Okay. So these filters, and then there is one special filter called the Laplacian. Okay, so the Laplacian filter in the frequency domain. So we will talk a little bit about this, and this is also like highly used filter. Okay, so I will talk about this next time. Okay, and with that we will end our discussion of frequency domain filtering. Okay, there are two effects uh, that I have to talk about. So I talked about aliasing in the one-dimensional case, right? So we have to talk about aliasing in 2D, and we have to talk about Moir patterns. Okay, so these two effects also I will talk about next time, and we will see how this filtering in the frequency domain can help us get rid of these kind of artifacts that appear in images. Okay.